Welcome. Today we're going to look at the issue of imbalanced data. It's incredibly important to realize that imbalanced data has to be seen in the larger issue of data itself. Now, obviously, we need to get good data, because if not, regardless of what type of model we're building, be it a discrete simulation model or a machine learning model or artificial neural net, wherever it may be, having bad data is not going to help us. As the saying goes, garbage in, garbage out. And so we need to really consider imbalanced data as in part of the issue of data in general. So obviously the steps are, we need to actually get a data set that's useful. We need to figure out what are the underlying characteristics like distribution and features. We need to make sure the data is clean, meaning that we're not missing a lot of elements, actual samples, and also that it's not dirty. Maybe we have wrong data values in there. We're going to be able to take that data, and then we're going to have to split it into both training and test sets. And then from there, we're going to figure out what features are necessary for us to build good models. This may include that we need to standardize or normalize our models. In this case, we're going to make sure that they make some type of sense in terms of comparison to each other. But the major thing we're going to issue today is the issue of pre-processing of unbalanced data. Most of our work in pre-processing is towards imbalanced data. And that'll include looking at several techniques of oversampling, undersampling, creating synthetic data where it's a useful tool, or even weighing the data to make it acceptable for our use. So keep in mind, we're looking at mostly imbalanced data, but the concept has to be considered as part of the larger issue of making sure our data is acceptable for modeling. So we have the other steps, cross-validating, making sure that the model itself is performing well, making sure we select a good model, training the model, making sure whatever parameters we use for it make the model better as we keep working with it. We're going to need to evaluate these models. At the end of this, we're going to revise them either by post-processing, which is basically we optimize, and also iterating and monitoring how well the model performs altogether. As stated, though, we are going to look at imbalanced data, which are cases in which we have one class of data that's usually much greater than all the rest of the data. It kind of makes sense. For example, we do not want a lot of fraud cases. So we are probably going to want to see much less data on the fraud and have more fraud cases that are not fraud. Same thing with spam. We want more cases of not spam than spam, or even disease. The issue is, though, that typically in such cases, we have to consider the fact that if it's no fraud, and there's a vast majority of that, that may cause us problems in terms of developing out good metrics for them. So for example, if we have data samples of non-fraudulent transactions, we probably have a lot of them. In this case, for our sample, we'll say we have 9,000 fraud transactions. We may also have 400 that are actual fraudulent transactions, or at least identify them as such. But the issue is we now have a case in which about 4% of our fraudulent transactions are represented by the data. Now, simply by being such a small proportion, we could literally just make code that says, put in whatever data and just return no fraud. And by simple numbers, the accuracy of prediction of a model like that would be close to 96%. Why is that? Well, it simply has to do with the fact that almost 96% of our data is by its very nature already predicting not fraud. And as a result, for the non-fraud transactions, we'll have a 100% accuracy rate. But for fraudulent cases, we would actually have a 0 rate. As a result, our model would be really good at predicting not fraudulent cases just simply by the nature of the data, but it would be a bad model in and of itself. So we need to consider that. One way we can deal with this is to take a look at our performance metrics. And you may have heard of the idea of the confusion matrix, which is basically it compares our predictions and the type of incorrect predictions, such as we find a good measure that classifies whatever we built. Three of the more common things we see are called precision, recall, or sensitivity, and the F1 score. In case of precision, the idea we're asking is, are we getting true predictions that are actually good? In other words, are we getting values back that are in and of themselves good predictions? Note how it says here, the percentage of true positive predictions compared to all positive predictions. So we're capturing what's necessary. The problem is that with low precision, that means that we have false positive predictions. So that may be something that we need to consider. In terms of sensitivity and recall, which is basically trying true predictions that are finding all true cases, we are more concerned about whether or not we're getting false positives, or false negatives, actually. So notice here it says true positive rates, percentage of true positive predictions compared to all actual positives. So the idea for precision is more when we're predicting something, are we getting actual good predictions of a true case? Whereas recall is basically saying, are we capturing those cases that are actually important? The F1 score tries to look at a balance between the precision and recall, as we'll see, and these values are represented here, but it probably makes more sense if we look at a sample. So in this case, we have, it could be anything. It could be capturing cases of cancer, or it could be capturing spam or whatever. But notice the way in which the data is set out. We have actual cases where we predict correctly, 30-some. We have cases where the actual case is negative, but we predicted positive, false positives. We have cases where we had positive, but we predicted negative, false positive. And then we have negative where we predicted negative, true negative. Note, though, the values that come out of this. In terms of accurate predictions, we find that we have about a 96% accuracy rate. The issue is, note that there's a vast disparity between the number of negative predicted as negative and positive predicted as positive. So we cannot just go with accuracy, so we have to look at both precision and recall. And typically that's what you'll see out there. So when we talk about precision, notice that if we look at precision, which is basically we look at how many are positive and actually predicted as positive, and how many are negative but are predicted as positive, we see that we're predicting the truth when we find positive or predict positive of about 50%. So we're getting an awful lot of false negatives, or false positive, I should say. In this case, though, notice, when we have the recall, we're predicting the value, but of all those cases that are actually positive, we're actually predicting a fair number of those. That's around 75%, because the idea is of 40 cases that we predict, 30 of those are actually positive cases, and therefore we're actually predicting and catching these cases fairly well. The problem is when we're predicting, about half of those are false. So it's key to remember that depending on what you need for a given model, precision and recall are actually two of the best examples for you to look at in terms of your metrics to figure out whether or not your model is good. That will help us when we look at the Imbalanced Data and to figure out whether or not they're good models. A second way to look at these is to use different algorithms. Now remember, because the difference in data we need to compensate for the fact that we might have very limited data of one class versus another. One of the ways you can do that is through things such as decision trees and random forests, because they actually are pretty good working on imbalanced data because they're more of looking at if-else issues, and as a result, they're capable of taking data and making them into decision nodes. In this case, you'll notice on the left side, we have a very simple representation of a decision tree. And on the right side, we have a simple representation of a random forest. The idea is that each of these nodes will help us look at different classifiers in the data to make it worth our while. So algorithm change might be one way in which to address issues of imbalanced data. More often, though, what we'll see is we're going to resample. Now, resampling basically means that either one, we're going to get less of the data from the majority of class, usually by removing, or two, we're going to have more emphasis on the minority class and basically blow that up to be closer to the larger majority set. So these are simple illustrations of that. But notice that with the undersampling, we're taking this and condensing it so that we have about equal representations between the majority class and the minority. In oversampling, we do it the other way. We take the small minority class and basically we generate synthetic data for the most part, and we'll see how that's done. But the idea is we need to make the set balanced so that whatever's trained is able to understand what the values are. Because if you see so few cases, you're not going to be able to make good predictions. In oversampling, we have copies of minority cases. So what will happen is if you have a small data set, which means you can't lose much data, you will probably want to use an oversampling method. Note though, you have to split the data into test and training sets before you sample. The reason is you'll have the same sets if you don't. It will cause you to overfit whatever you're working on. The generalized model will be very poor because what it'll do is it'll basically be seeing the same data over and over and memorize it. And as a result, you're not going to get a good match. So that's why we talk about poorly generalized model, because it memorized the model and will have problems. For those of you interested in using a method like this, Python does have oversampling ones. And this is the general model here. It also has a random sampler. What a random sampler basically does is it goes through and it randomly takes a set for the minority and uses that to build. You see much more, though, about majority classes being undersampled. And what that means is take sections of the majority class and use those and make them smaller so that they match more of the minority set, minority class. So notice how it talks about we remove observations. This is good if you have just a ton of data, millions of rows, quite literally. The problem with this, though, is because you're removing data, there's a problem with possible underfitting and even generalization. Because obviously, if you take data away, you might be losing certain elements. And so for comparison, we notice that if we oversample, it's great because you don't lose information. You're generating it. Only problem is you might be undersampling and you might be overfitting as a result. In the undersampling case, though, it can be good because you have less data to look at. The problem is you might underfit the model, and as a result, the generalization of this model will be very poor. Now, I have to reiterate something. In underfitting the model, basically, you're not capturing where the particular features are needed to make a good classifier. In overfitting, you're basically fitting so well that any new data being checked probably is not going to perform all that great. So regardless of the method you use, you always have to be careful and think about these issues. If I'm going to oversample, I might overfit the model. So I can't use new model data really easily. If I undersample, the problem is because I'm underfitting naturally, I'm losing data. It may bias my sample, and therefore it's not an accurate representation. And finally, the end result is simply I'm not classifying as it should be. The data just is not representing what's actually there. That said, there are some techniques that are relatively good. But keep in mind, whenever you use them, you need to make sure you understand the underlying issues that could be there and check for them. So some of the techniques for undersampling include random sampling. So the idea is I just take random parts from the majority class and create a balanced data set with the minority class. As you see here, there's a Python example, which is the random undersampler. I could do what's called cluster centroids. And what that does is it says, develop out clusters in your majority class, make them into centroids. Basically, we're talking about impulse areas. So you're basically making a point that represents clusters rather than the actual data. So that kind of captures some of the underlying distributions of that. And by doing that, you're reducing the number of clusters down to a single point that tries to represent all of them. And you see here that Python will also do that for you under the case of cluster centroid method. Another example is the near-miss algorithm. Near-miss will basically sample from the majority class in such a way that whatever is closest to the minority are considered, and it allows you to keep a subset of that majority class. I'm not going under these in incredible detail because we can cover them in more detail later, but I just want you to get a feel for what some of the elements are. And mind you, if you want to, you can play with the different algorithms yourself. That's why I provided these examples for you. But keep in mind that regardless of which one you're using, you need to remember that they are undersampling whatever you're working with. Some of the other ones, and I'm going to explain these in a little bit more detail because they can be useful, is the idea of tomic links. So what tomic link does, interestingly enough, is it says, let's look at the nearest neighbors, the tomic link. So you see here that you have two classes. And it says, whichever ones are closest to each other, go to those and basically remove from the larger class. The idea is, as we remove from the larger class, it makes a better separation between those. And in that sense, it basically increases the boundary between the two classes, or at least makes them more distinct. Interesting about tomic links, and the reason why I did want to mention a little bit more, is actually, even if you have balanced data, it's actually really good at removing noise in case you need to consider that within your data. So that could be something very interesting to consider. Going on. Another considered case could be the penalizing algorithms. The idea of a penalized algorithm is basically when you make your predictions, in those cases where the minority classes are misclassified, the algorithm is penalized, and it tries to basically over-represent the minority classes. So you see here it talks about using algorithms like penalize SVMs, support vector machines, increasing the cost of the classifier so that when it gets it wrong on minority class, it basically says, give more importance to the minority class. That's because it's underrepresented. It tries to get to a point where it's no longer underrepresented, and so that's where it tries to weigh them in terms of a penalty. Another example is the synthetic samples. Now, it's not quite like GANs, if you've heard of the technique, but it does do something very similar. What generate synthetic samples means is that we use techniques like SMOT, which is also considered an oversampling technique usually. And we find the k nearest neighbors, and using those k nearest neighbors, we generate synthetic data to train the models. Now note we have here, basic algorithm is we choose the minority as the vector. We then find the k nearest neighbors to that, and actually the SMOT algorithm will do that for you. We choose the neighbor to make the synthetic point, and then we can continue until the balance is found. So here's, for example, we have the minority class, and what it does is it says create new elements based upon the elements that we have already. So what we have here is, note, we have all these different ones that are in the minority class. And so what we do is we generate synthetic data based upon the nearest neighbor algorithm to be able to develop out a new element, new sample, such that it fills in the areas where we expect the data to be. In other words, it says, hey, data is supposed to be predicted as being here, so just by generating more samples in there, we're really not changing any of the boundaries. We just put samples that should be there anyway. Interesting technique, obviously, but you have to be careful because if they're not generated properly, you may have problems, but typically synthetic samples will have no issues. And with that, I thank you very much, and we'll go on with another test, another consideration in the future.